Okay, so what we're going to be doing in this video is I've got 4 different venturis printed off, and these numbers here is the diameter of this section here. On all of them, this diameter is the same and the outlet diameter is the same, but this part here has been changed and they start out at 0.2 inches and go up by 1/10 of an inch up to 1/2 an inch or 0.5 inches. So what I want to do with these is I'm going to take them out into the garage and set them up on my flow bench. What I want to find out is, at a specific flow rate, what's the pressure drop across these ports here on all 4 of them, and it'll be at the same flow rate for all 4. So that's one thing I want to find out, is at that specific flow rate, what's the pressure drop across here. The other thing I want to know is, what's the pressure drop across the entire venturi. Now, the reason I want to know that is because at that specific flow rate, the pressure drop across the whole thing will kind of represent the crankcase pressure. So the idea is that I don't want to have a venturi that's too restrictive and causes a lot of crankcase pressure, and that's the kind of the problem that you run into frequently when you're instrumenting something. It's like sometimes it's hard to instrument something without actually affecting the characteristics or the qualities of the thing that you're testing, and that can be kind of a difficulty sometimes. And so what I don't want to do is I don't want to have a venturi so restrictive that I end up with a lot of crankcase pressure. So those are the 2 things I want to find out for all 4 of them, and I'll record them and we'll have a look at all those results. The other thing that I've kind of changed I've done a little bit of testing already with another venturi, and just by the way, just from what I've seen so far, I think that my preliminary estimate of having a peak flow range of 0 to 25 CFM, I'm kind of thinking 25 CFM might be a little bit more than what I want. And so what I think I'm going to do is revise that down to 10 CFM. So I'm going to try to measure these pressure drops all at 10 CFM. Now, the problem that I'm going to be running into with that is that my flow bench was designed to flow cylinder heads, like intake and exhaust ports mostly. And because of that, those usually flow, upwards of 150 CFM, and my flow bench on the intake side can go up to almost like 400 CFM at 28 inches of water. So the test flow range of my flow bench is way higher than what these are going to do. I've noticed, like, with some of the tests where I'm measuring the flow through the cylinder head at, like 50 thousandths valve lift, I've measured as low as 20 CFM before, or 20, maybe it was 25, 27 CFM. So it can go down, kind of down there, but the problem is the lower I go, the lower the flow rate is, probably the more inaccurate the number is going to be. But what I'll do is, it may not be exactly at 10 CFM for all of them, but I'm going to try to do all of them the same way. I can probably get myself pretty close to 10 CFM, but that's a problem in the way that I'm doing this. Another problem that I may be running into, we'll see, is the pressure range of these sensors that I got, and they were like 0 to 40 kPa, and that range might be too much for the pressure drops. So the pressure drops I'm going to see across here may only go up to maybe 2 to 10 kPa. So that's going to remain to be seen whether or not the range of pressures on this are too large for the pressures that I'm going to be seeing here. We'll try it out, and the way we're going to find that out is by testing it on the flow bench and seeing what these pressure drops are. And the other tool I'm going to be using is I have this, it's a digital manometer, and it works pretty good. And I think what these are for is like people in the HVAC field, you know, they sometimes need to be able to measure pressure differences and things. I think that's probably what this is for, but I think it ought to work pretty okay for what we're going to do today. So, at any rate, I think that's all I got to say about this. Let's get out to the garage and start trying some of these out. Alright, so this is that's the 0.2 Venturi. So what we're going to do is, like I said, we're gonna be measuring this pressure drop here through the Venturi and the pressure drop across the Venturi. And I know I've got that there, but it's out of the way pretty well. And I need that there and these weights on it because even at 1 psi, that plate's getting pushed up with a force of 12 to 15 pounds of force. So I can't hold this in place and do what I gotta do over here. So that's gotta be there like that. So anyway, like I said, we want the pressure drop across here and across here. So the way I'm going to get it across here, since this manometer is basically a delta P manometer and it's just measuring the pressure difference across these two ports, the idea is that if I want to know what the pressure difference is across this, I'm going to just leave one of them disconnected, that one disconnected, and leave that one connected. It'll basically be the pressure drop from here to here. So that's the way I'm going to do that. So we'll run the test with it hooked up like that and get the total delta P across the Venturi or the meter, and then we'll do it with that tube hooked up to here and get the Venturi delta P. This manometer here is the one that measures responsible for measuring the airflow rate through the flow meter on the flow bench. So, but what I'm kind of seeing is that when it's reading, so that's 0.1, that's 0.05, that's 0.01, but down here between 0.01 and 0 is where it should be about 10 CFM. So 0.005 inches of water. So 0.005 inches of water should be about 10 CFM, and you can kind of see why, you know, I'm having some trouble reading flow rates that low because it's way down here on the scale. And there's probably going to be some error involved in that, but I think I can get it pretty close. And then the other thing of it is, because the airflow rates are so low, I'm actually controlling. So I've got 6 vacuum motors for my flow bench, and for this I'm only using one of them, and even that spins too fast and flows too much air, so I'm using this speed controller so that I can bring those flow rates down far enough so that I can actually do what I need to do here. So let me run that up and I'll show you the manometer as the flow rates come up, and then we'll come back over here and I'll show you this. I wish I could do 2 camera views at the same time, but it's not gonna happen today. So the first one we're gonna do is the total pressure drop across the Venturi, or across the meter. So let's look over here. You'll probably be able to, I'm sure you'll be able to hear the motor. About as good as I can get it. So that pressure drop we saw across the flow meter, the flow bench flow meter manometer, was about .005. That was about as close as I could get it, and we were reading about 16.5 on this. So I'll record that, and then we can move on to this other part. Okay, so now that's hooked up like that. Now let's basically run the same thing with it hooked up like that. Okay, so what you can see there is that through that, it said there was an error, and basically what happened is it overranged the manometer that I've got. So on this particular meter, we're going to kind of have to, we're going to be limited by that on this meter and this manometer. So this, we'll do it again. I'll bring it up as high as I can, and we'll see kind of what it was reading on the other manometer. So I would say on that manometer it was probably reading a little less than .005, but I think that's just where I'm going to have to be able to, I'm going to have to just deal with it like that, I'm afraid. So what was it reading about? I think we got to about 21. And of course these are kPAs there. So, yeah, I'm kind of limited in terms of my manometer here, in terms of what I can measure there. But we'll just take that for what it is, and, well, we're just going to have to deal with that. So now what I'm going to do is I'm going to do the same thing with the other 4 venturis that I've got. And we'll see how they go. I'm not going to bore you with recording that. And I know that this corner of my garage is just not very well lit. So whatever. So I'll do the same test on the other 4 or the other 3 venturis, and then we'll take them and we'll take those inside. We'll enter them into the spreadsheet, and we can see what kind of where we're standing, which one of these might be best suited for what we're trying to do here. So let me do that, and then we'll look over the results. So I got done doing the flow tests on those four Venturi meters that I made. Started entering the data into this spreadsheet, and here are the results from those 4 flow tests. Now, what we're gonna, so in this data here, what I was targeting was 10 CFM on the flow bench. So that's what I was trying to go for, but we saw out there in the garage that manometer really wasn't. The manometer and the flow bench itself really isn't intended to measure flow rates this low. There's the 4 different venturis to test, and here's the parameters that I either measured directly or calculated. So this Venturi delta P, that was the pressure change that happened in the middle of the Venturi, where it kind of narrows down in the middle. And so that's what that one is. This one here is across from the beginning of the meter to the end of the meter. And I told you about how I was measuring those 2 things. So, and these are the calculated values that I used, that I calculated from this spreadsheet. And so that's the measured flow CFM that calculated from the Venturi itself, the Venturi meter itself. And these are the velocities of the pipe. So that would be the upstream, like the velocity upstream of the restriction in the Venturi. That would be the velocity of the flow in the restriction in the Venturi itself. And I've added in the Reynolds numbers for these, and I know I haven't talked about that yet before, but basically what for me, what the Reynolds number is kind of a way of gauging what the nature of the flow is, whether it's going to be um, laminar flow or transitional flow or turbulent flow. And generally speaking, Reynolds numbers below 2300 they tend to be laminar, and Reynolds numbers between 2300 and 4000 tend to be transitional. And the Reynolds numbers above 4000 they're probably going to be fully turbulent. And you can see that all my Reynolds numbers that I calculated here are well above 4000. So the flow everywhere in my Venturi should be fully turbulent. Now, I calculated the Reynolds numbers in a couple of different places. Now, the lower number is basically the pipe diameter upstream of the restriction of the Venturi. And the way I read it, that's kind of where you're supposed to measure that or calculate that from. But I thought that it was also kind of sort of important to know what it was in the restriction in the Venturi itself. So I added those there just for reference, just to have them. So, but they're all well above 4000, and it's fully turbulent. Now, the other thing about the Reynolds number is that in a Venturi, it might change what you choose for your discharge coefficient. So there's a table I found on the Engineering Toolbox website that I told you about before, and with these Reynolds numbers, I chose to go with a discharge coefficient of it's up here. For all of them, I chose 0.96. And I think that that's probably okay, even though that maybe that number might be a little bit higher. But I tried it with that and the 0.98, and it really doesn't change things very much. It does change things, but not dramatically. But with the table I looked at, and I just kind of decided to go with a 0.96 for the discharge coefficient, and I used that discharge coefficient for all 4 Venturi meters, even though there's a possibility it might be a little higher or lower than that. So, but 0.96 I think is probably going to be probably going to be okay. So that's what I'm going to go with. It's a 0.96 discharge coefficient. And then down here, I calculated the Mach number. I calculated these Mach numbers based on these flow velocities here, and I calculated them both in the upstream diameter of the pipe going into the Venturi and the restriction portion of the Venturi itself. Start with this 0.2 Venturi. Now the problem I had with that one is that you can kind of see here that I didn't quite get to 10 CFM on that one. And part of the reason I couldn't calculate it was a couple of different reasons. The Venturi itself was enough of a restriction that one vacuum motor couldn't pull enough of a vacuum to flow that through there. And it wouldn't have mattered anyway, because the manometer I was using kind of started going into an error once the delta P across it got above, it started having problems around 20 kPa. So after it went above 20 kPa, it started erroring out, and that was about as high as I could measure it. That's what I got there, and what I'm seeing here is that even at that flow rate, you need to have about a 2.4 psi pressure drop across the whole meter. So that would mean to flow that and have that flow rate coming from the pressure coming out of a crankcase, it would mean you'd have to be up around 2.4 psi in your crankcase in order to get to that flow rate, which that might not be crazy high, but it's not, I don't know if that would be acceptable or not. It might be. I did some research around and just looked around what acceptable crankcase pressures are, and I saw some people saying as high as 4 and 5 psi is what you can kind of deal with. I'm going to be finding this stuff out in the future as I go, and we'll find out. When it comes to the Mach number in a Venturi, we talked about before that you want to keep that below 0.3, but they don't say where in the Venturi. I didn't see where in the Venturi they said you measure that from. But on here, in the restriction of the Venturi, we can see that the Mach number here is it's 0.5, which is above 0.3. So I'm kind of wondering, maybe this isn't, maybe this Venturi here is just a little bit too small for what we're going to be doing. And so that's kind of what I think about this one. I think this one's a little bit too small to work good. On the other hand, the thing I like about it is that the range of pressures here would fit really nicely into that range of pressures that the pressure transducer can read in. So that's one thing I like about it, but the downside of it is that I think it's just a little bit too small, and maybe the delta P across it is a little bit too high. So, but going on to the 0.3 Venturi, we're getting like 12,000 measured that way, which I think that's pretty good. I think that would work that would probably be okay with that transducer I've got. We're showing at that flow rate, which was, what did we have, 13.4, which, you know, that seems a reasonable number to me. And at that flow rate, we're getting like a 0.9, so that'd be like 0.9 psi of crankcase pressure, which I think that's tolerable. I think I could tolerate that. But anyway, I don't know, like I said, I don't know what, but that seems like, maybe it's okay. So I like this number seems okay, that number seems okay. Okay, we got those. Reynolds numbers are about a little bit higher. And the Mach number on this one, because it was smaller here, the Mach number came down to 0.4, which is a little bit high. But then again, this number is a little bit higher than the 10 number that I was looking for. So that might come down a little bit. And so I'm kind of liking this one. The only thing I don't like about it is this is the Mach number on that one. So, and like I said, I don't know if that's even the right place to calculate the Venturi Mach number from either. So, but that's the way I'm going to look at it. And as we go up into the 0.4 Venturi, 0.4 inch diameter Venturi, we see that the pressure drop, you know, measured that way, has come down to like 4,500 pascals or 4.5 kilopascals, which is kind of getting down to the lower end of the pressure transducers that I have. So that might be okay. That might work there. So, but these are things that I can find out. We can try. And then the thing I do like about this one is that at that flow rate, the pressure drop across the Venturi is pretty low. It's lower. So that would mean like 0.3 psi of crankcase pressure at that flow rate. And that flow rate was 14.4 CFM. So there's things I like about this one, and there's things that I kind of like about this one. And especially the other thing about this one is that the Mach number inside the Venturi has come down below 0.3, so that's kind of a good thing there. So that's the things I got going on in that one. And then in this one, I think this one might be a little bit too big, because now we're way down to like 1.9 kilopascals. So that would be way down at the bottom of the range of that pressure transducer that I've got. And again, here I like that number better. The flow rates are about the same, and the Mach numbers are down into a reasonable area there too. So there's things I like about each one of the Venturis, and there's things that I don't like about each of the Venturis. But what I'm thinking is that probably the one I'm going to go with is probably either this one or this one. I'm probably going to go with this one. It's probably where I'm going to start. The next video is probably going to be about getting those pressure transducers hooked up to the computer. And the computers that I have inside my data acquisition system there's 2 Raspberry Pis in there, and I got another one coming. So I'm going to try to, that'll be the next video. We're going to try to get those connected in there and start reading some pressures in, and get some, it looks like I found a program that might work for it, so we'll have to get that, try it out, and see if we can get some flow numbers reading into the computer. And if we can get that going, that would be pretty nice. Well, I guess that's about all I've got for this week, so I guess we'll see you next time.